they're grown in eggs. And this is, oh my gosh, this is so painstaking. And usually it takes about 6 months before you can make sufficient vaccine to start vaccinating the public. So in normal years, what they have to do is guess 6 months ahead of time which 3 influenza strains do we think are going to be the epidemic strains. And it's guesswork. What they often do is look at the southern hemisphere. They look at Australia, New Zealand, find out which strains are circulating in the southern hemisphere, and they make the guess. They say, well, we think, there's high probability that maybe 2 of those strains will become the epidemic strains in North America. But it's a total guess. Some years they guess right, and some years they guess wrong. But they have to guess 6 months ahead of time. So one thing that we really need is technology that will speed up vaccine production. So, there's a pandemic, it starts, ideally if we could start making a good amount of vaccine in less than a month, that would help a lot. Yeah.
Is that possibly why, sometimes when you get the vaccine, you still get sick?
Yes, yeah. And some years they're way off. Some years what happens is that 3 strains in the vaccine, none of those strains end up causing an epidemic. It's a 4th strain that's not in the vaccine. And so that's why a lot of times you may still get the influenza, even if you've been vaccinated. One hope is there might be some cross-reactive protection. So if you're vaccinated, they guess wrong. Hopefully some of those antibodies we produced against a vaccine strain might offer partial protection against a different strain. Yeah, so for me, I always get the vaccine strain. Those of you going into healthcare, you're going to be exposed to lots of sick people. It's probably going to be highly recommended that you guys get vaccinated every year too. Yeah.
Can the vaccine itself make you sick?
That's such a great question. The most common strain that's inoculated, the viruses are killed. So the viruses can't cause you to have influenza, but what can happen is part of the immune response, your white blood cells release all these chemical messengers, these cytokines, and those cytokines often are what cause the flu-like symptoms, ache, pain, malaise, headache. So even though you're not actually suffering from influenza infections, you're getting some of the same chemical messengers released that make you feel like you have the flu. So a lot of folks say, yeah, the flu vaccine gave me the flu. Well, it's like they weren't infected, but they had the symptoms of the flu. And also some folks perhaps were already infected before they got vaccinated. And it might have been like a coincidence that they were already incubating, and then they broke with the clinical signs and symptoms right after they were vaccinated. So that's another possibility, yeah. But the injected vaccine, the viruses are killed, they're inactivated, so they can't infect you. The intranasal vaccine, that is a modified live vaccine, and you always have to be a little bit careful with modified live vaccines because, especially with RNA viruses, some of them can revert to virulence. We'll discuss that with the polio vaccine. That's exactly what's happening with the polio vaccine. Those modified live viruses are reverting to virulence and causing polio. So we've presented the nightmare scenario, right? So what I want to do, because I start thinking about this stuff and I can't go to sleep at night. So one reason, I hope, is this little article, and I wanted to explore with you why some microbiologists, some virologists think that this won't happen. Some microbiologists, virologists think that this recombination event that would lead to this nightmare recombinant between human and avian influenza that has high transmission between humans and high mortality rates. Some microbiologists think it won't happen, and we want to explore why. So we can sleep that at night, and then we'll explore how other folks think that these folks are not well founded. Okay, so this article that we passed out, this is from the American Society for Microbiology. They have a monthly magazine, and they always have really cool articles in it. So it's from the ASM magazine for the microbe. And what this article is exploring is post-specificity is which tissues, which cells, which organs will the virus infect. So, you all remember that we said the H antigen is the adhesin, and it binds to the sialic acid residues on the surface of epithelial cells. Okay. So it turns out there's different, I guess we could say different forms of sialic acid, how they're linked to other components of the cell surface. And I'm just going to simplify it, you guys. So we're just going to say there's different types of sialic acid. That's probably oversimplifying it. The types are really how they're linked to other components, but we'll just try to simplify our life. So the two examples that we'll use are sialic acid, and we'll just call them sialic acid 2,3, and I'll put SA for sialic acid, and sialic acid 2,6. And again, this just reflects their linkage, but we'll say they're two different types of sialic acid. And what's really cool, you guys, I mean, this is a whole area I have, really no idea, and I'm like, oh, I'd love to get into this more, is it turns out that different animals have different types of sialic acid, and even within an organism, there's different types of sialic acid in different parts of the body. So in my goofy little cartoon, you guys, down below here, that's supposed to represent a cartoon of the human respiratory tract. And as you guys can tell, this is why they have never asked me to teach anatomy, because of my horrible cartooning skills. Okay, so we're going to pretend, you guys, that this is the human respiratory tract. And this tube up here would represent the upper respiratory tract, the trachea. And these two blobs down here represent the lower respiratory tract, the lungs. Okay. And the trachea acts as a conduit for air that's inhaled and then air that's expired. It also has that beautiful mucociliary escalator, so it's an important part of normal defenses to protect us against all the junk and microbes we inhale. The lungs are where the real important part of the respiratory tract occurs. The lungs is where gas exchange occurs. So oxygen from the air we inhale diffuses across the alveoli, across the capillary walls, and then are absorbed by the red blood cells to deliver the oxygen to other tissues in the body. And then when the blood is returned, the blood is carrying carbon dioxide, for example. The carbon dioxide is released and diffuses into the lung space and is exhaled. So the real functioning part of the respiratory tract is occurring down here in the lungs, in the lower respiratory tract. Okay, here's the coolest thing, you guys. So it turns out in humans, the respiratory epithelial cells in the upper respiratory tract have the alpha-2,6. Make sure I don't mess this up. Alpha-2,6 sialic acid residues. But in the lungs, the epithelial cells have the alpha-2,3 sialic acid residues. Okay. Now, it turns out that most human influenza strains most of these guys, you remember we said that there's high transmission person to person, but what about mortality rates? Usually most of them have low mortality rates, low virulence. And one reason to explain this is most of these human adapted strains bind to which sialic acid receptors? Which types do you think they bind to? 2,6 or 2,3?
2,3.
Most of them are adapted to bind to alpha-2,6, okay? Most bind the alpha-2,6 sialic acid residues, okay? So if we use, we'll just use a little white asterisk to represent influenza virus. So when we inhale these human adapted strains, to which cells are those influenza viruses binding, infecting, and then replicating in? Usually it's cells in the upper respiratory tract, right? So they bind to the cells of the upper respiratory tract, they replicate, they release, hundreds and thousands of new influenza virus. So when we're sick and we cough and we sneeze, we're spewing out thousands and millions of influenza virus, right? right into the face of our colleagues, right? Our family members, our friends. So this explains the high transmission rate, right? But because they're replicating high in the respiratory tract, right, they are definitely damaging our beautiful ciliated cells, yeah? So they're causing damage to that mucociliary escalator. That means we're going to be at much higher risk for, say, bacterial pneumonia, right? But usually the human adapted strains, they're replicating high up. Usually they're not going to cause any harm to the gas exchange lower down, right? Because they don't attach down there, right? Okay. So that explains high transmission but low virulence. Virulence meaning severity of disease, low mortality rates, right? Okay. Now here's the scary part. Well, not scary. It's actually good. I mean, sort of good. Okay. So remember our ducks, our birds, right? And what is a rich source of influenza virus? And ducks. And yeah, right. So those avian strains are adapted. The avian strains are adapted to infect and replicate in the bird's intestinal tract. And what kind of sialic acid receptors do you think the bird's intestinal tract has? Alpha 2,3, right? So these strains are going to bind to the alpha 2,3 sialic acid residues, right? Rich in the intestinal epithelial of birds. So when those birds poop, okay, when they poop, and we find the influenza virus in the feces, and let's say a human has bought this bird and is going to take it home to slaughter it, or maybe it's a wild bird that somebody shot, so they're going to butcher it and eat it. Okay? And let's say that in that slaughtering or butchering process, they inhale some of those avian influenza from the feces. Okay, so here comes an avian influenza. Now, where will these avian influenza bind? Are they going to bind in the upper respiratory tract to the alpha 2,6, or are they going to bind? They're going to bind lower. They're going to bind in the lower respiratory tract. Okay, so this is where the avian influenza are going to replicate. And what happens is they're replicating in the epithelial cells in the alveoli. They're causing profound inflammation. You get leakage of fluids into the lungs. That fluid interferes with gas exchange. The inflammatory changes. You're going to recruit white blood cells into the lungs. This inflammatory and then cell-mediated response, it's going to incredibly decrease lung function. So you're going to get a decrease in gas exchange. Okay, so there's these horrible descriptions of people drowning in their own fluids, yeah, and having blood-tinged sputum, because they're hemorrhaging in their lungs and they're drowning in their lungs, right? So these avian strains are going to have high or low mortality in humans. High, right, okay? But here's the thing, you guys. So these avian strains, high mortality in humans, right? Because they're replicating low down. But here's the thing. My cartoon doesn't of course do justice. But my cartoon is totally wrong, right? The lower respiratory tract, it's not just these balloons at the end of the trachea, right? There's these incredibly branched airways, right? These branching airways. So for these replicated avian influenza to make it back to the trachea and up and out when we cough or sneeze, they have this incredibly tortuous path, these branching pathways. And as a consequence, when we're infected with avian influenza, when we cough or sneeze, not many of these avian influenza can make it up, to the trachea and out. And as a result, we have much lower transmission when folks are infected with avian influenza, right? So we're going to get low transmission because not many of the avian influenza virus can work their way from the lungs, from those alveoli up to the trachea and out. So what some microbiologists have said is that if we ever got a recombination event between human influenza and avian influenza, if we got a recombinant that had high transmission between humans, they say, well, that recombinant is gonna be replicating where? To have high transmission between humans, this model suggests the replication, if this was our recombinant, this model suggests to have high transmission between humans, you're gonna have replication high in the respiratory tract. And consequently, you have a trade-off. You have increased transmission, but you have lower mortality rates, right? So I wanted just to share this with you to say that some microbiologists are hopeful that we won't end up with a combination human influenza, avian influenza, that's highly contagious between people and has high mortality rates. Now, it turns out, of course, other microbiologists disagree, and one of the reasons is that that H1N1 strain of that 1919 strain, that H1N1, it had high transmission and high mortality. Okay, so it's obviously possible for human strains to develop both high transmission and high mortality. For those of you that might be interested, I know none of you have any free time, maybe this summer if you have free time, this is a book I'm reading right now. Gina Colada, she's a writer for the New York Times, so it reads like almost like fiction, but she's going through the history of influenza from ancient times through the 1918 time, through the first part of the avian influenza outbreak. And what's really fascinating, you guys, is researchers have been able to go back and take preserved tissues from people that died of the 1918 strain. They went up to the Arctic Circle and they got permission from family members to dig up bodies of people that had died in the 1918 pandemic. And since those bodies were buried in permafrost, the bodies have been pretty well preserved. They were able to harvest enough tissue from the bodies of people that had died in the 1918 strain. They actually have got the complete RNA sequence of the 1918 strain. And there's a couple of hypotheses as to why that strain was so virulent. And one of the hypotheses was, so why was it so virulent? Okay, so the question is why? Okay, this kind of violates our model over here. So one hypothesis is that it spread to the central nervous system, which is unlike most of the normal human strains. Most of the human strains are confined to the lungs. There's actually an enzyme in our lungs that has to cleave one of the influenza proteins to activate it. And in humans, that enzyme is only present in our lungs. But there's some thought that this was a unique strain that had the capability of using other of our enzymes, for example, in the nervous system to cleave this protein. So there's one hypothesis that it was capable of spreading the central nervous system. That was one hypothesis. Another hypothesis was that it triggered an extreme immune response, and that it wasn't actually the virus, replicating in the cells that killed people. It was the immune response. It was this exaggerated immune response, and so it was actually an immune response mediated problem. And then another hypothesis is one of the genes in influenza virus makes a protein. It's called the NS1 protein, and this NS1 protein has been found it can interfere with part of our normal response to viruses called interferon. So this lowers the host cell interferon response, which is part of our normal defenses against viruses. Okay, so work continues to try to understand why that 1918 strain was so virulent and had such incredible high transmission, because they need to understand that so that we can be better prepared for when, eventually, and all the public health folks say it's going to happen, we will get a repeat of like the 1918 pandemic. Now the good news is, you guys, we now have antiviral drugs, right? So they found out the 1918 strain, when they reconstructed it, it is sensitive to Tamiflu, for example. we have now antibiotics to help protect folks. Many of the folks that didn't die from the influenza in 1918, they ended up dying from secondary bacterial pneumonia. So now we have antibiotics to cover those folks. Remember, just to tie some things together, remember it was as a consequence of that 1918 pandemic that Frederick Griffith was working with Streptococcus pneumonia trying to develop a vaccine to protect people against the secondary bacterial pneumonia. Okay, so we have antibiotics to cover that, and we have better medical facilities. But the concern is that if we have a pandemic, our hospitals will be overwhelmed. A lot of the doctors, nurses, healthcare providers will be sick themselves. So it's going to be a matter of who will get access to the drugs, who will get access to the hospitals, right? And we already know here, right, at home, even without a pandemic, most of us don't have access to good medical care, right? So can you imagine if a pandemic comes along? Yeah, pretty grim, huh? So hopefully they'll continue to explore how these viruses can be so virulent, and hopefully there'll be continued research into antiviral drugs, so we'll have more weapons on hand. Okay, well that wasn't too cheery, was it, you guys? Okay, so let's see what we got here. Let me just go back here. Whoops, let me go back just really quick, just so we can finish out these slides. This is just a cartoon of antigenic drift. So you guys remember those are the small changes and the H and N antigen that cause for mutation. So here what the artist did was we have kind of a turquoise-looking influenza infecting this cell. During replication, mistakes are made by RNA polymerase. So we did some minor changes in the H and N antigens. So we just see a slight color, so bluer virus is being released. So that's antigenic shift. Oh gosh, I said it wrong again, guys. I'm so sorry. Taper fingers so long. That's antigenic drift, like driftwoods, little tiny changes in position. And it's believed that antigenic drift is responsible for local epidemics about every 2 or 3 years. So this is just following time against the number of cases. And so again, every 2 to 3 years we'll have little local epidemics, and it's presumed that comes from antigenic drift. And then we had the recombination leading to antigenic shift. It's believed that antigenic shift is responsible for pandemics about every 20 to 30 years. And at the time of the 2009 pandemic, we were overdue for our next pandemic. You know, it had been more than 20 years, so people were prepared. This is just to show this will be an issue we'll deal with, like how to hospitalize all the folks that could become sick. This is from the 1918 strain, where churches, schools were converted into hospitals to help take care of the folks. And you can see back in the 1918s, they were using sheets and cloth masks to try to prevent transmission. And it's better than nothing. I mean, that's my thought is people laugh at it, but it's like, it's something, And this is something for you all to remember. If you are bird hunters here in California, there's a lot of bird hunting, bird hunters, bird hunting clubs. Oh yeah, I should talk about this. So here in California, here in Sacramento, we're on the Pacific Flyway for migratory birds that migrate from Central South America up through North America up to Alaska. During the summertime, they'll go up to Alaska. And the reason we're a little bit concerned about that is there's another flyway where birds from Asia, Southeast Asia, they fly up, and they too will overwinter in Alaska in the Arctic Circle. So birds that come from Southeast Asia and Asia, and there's great concern that that might be where a lot of these recombination events are going on with avian influenza. Migratory birds can carry the avian influenza up to those summer nesting grounds and mingle with the birds that will then fly south through California on down to Central and South America. So it's thought that if we get avian influenza, California is a potential hotspot, right, with the flyways. So, just remember that, you guys, if you have friends that are wild bird hunters, duck or geese, they'll have to be incredibly careful because they might end up being the first cases, right? And then if you go traveling in many parts of the world, you don't buy your chicken shrink wrapped in plastic, right? You go to a live bird market, you choose your chicken or your duck, and you take it home, and when you're ready to eat it, you slaughter it, right? Well, I remember as a little kid, my mom's family came from this little tiny ranch farm in the Rocky Mountains. We'd go back to visit, and as a special treat, my Aunt Margaret would go out and grab one of the hens and chop its head off and prepare it. And it was a long, long process. I was really impressed with how long it took. And also I was impressed by how she got splattered with blood and feces, all kinds of tissues, right? So when you're slaughtering birds, there's incredible chance for you to be exposed to avian influenza virus. Just figure, feces, any of the body secretions are infectious. So this is something for us all to be aware of. When you go traveling, if you should be careful of the live bird markets. It was 1997 in Hong Kong, and the live bird markets, where the first documented transmission, it turns out probably H5N1 had been infecting people in Asia for many years, but this was the first documented case. It was Hong Kong, 1997, was the first documented jump of H5N1 from birds to people. And I know this sounds really cruel, you guys, and insensitive, but I really admire the Hong Kong government, because when it was documented, they said it was causing such high mortality rates that government said we're going to slaughter all the birds. And I know that sounds heartless, but when you're faced with a pathogen that causes 50 to 60% mortality in humans, and they didn't know at that time, they were afraid it was transmissible between humans, the government went in and said we're going to slaughter all the birds to see if we can eradicate this. So it did stop that particular outbreak, but then as we know, H5N1 continued to pop up now all around the world, and with migratory birds carrying it, I think it's just a matter of time before we probably will have it here in North America and California. So it's just something for us to remember. Okay, on to other happy pathogens. Okay, before we do, guys, any comments or, oh my gosh. I know that was a lot on influenza virus, you guys, but I think this could be the big one in our, maybe not my lifetime, but in your lifetimes, it could be influenza might be the big one. Yeah, so I think it's really good we know. Okay, well, this is sort of a happier note. The rabies virus, we have a really good vaccine. So this is an RNA viral disease that we can prevent through vaccination. We have rabies virus here, endemic in California, so this is one we really want to have a handle on. So rabies virus, single-strand RNA virus, and this is really interesting, you guys. Here it's an RNA virus, but it's relatively stable. We've got a vaccine that seems to work year after year after year. So when we say RNA virus, we want to think potential for a high mutation rate, but it might be that in nature, the mutants are infectious, right? And that might be the story with the rabies virus. The mutants just aren't infectious for some reason. Good news, it is an envelope virus. So if it's shed from the host, and classically, the virus is transmitted in saliva of infected animals. Once the virus dries in the environment, it's no longer infectious. So usually we think of it, most commonly we think of it associated with a bite from a rabid animal. But we also need to be careful if you guys are, any of you are spelunkers, cave explorers? Am I using the right term? I know there's this cool term for people that love to explore caves. A lot of folks do that as a sport. You have to be careful because bats here in California are important reservoirs for rabies, and they think that some people have been infected by going into caves where bats are roosting, and the urine, the feces, the saliva, because bats will groom one another. It might be that saliva can create aerosols that may potentially infect people. So be careful if you're exploring caves where bats are roosting. So the rabies virus, these are some of the common reservoirs. So skunks are big ones, back east, raccoons, and I always get my animals confused. Coyote, you guys think? And maybe fox here. And one of the big ones that is missing for California are bats, right? So some people said, well, we should just kill all the bats, but ecologically that would be a disaster, you guys. Bats are so beneficial. They eat a lot of harmful insects, a lot of mosquitoes that can carry disease. So saying, oh, we'll just kill all the bats, that would be an ecological disaster. What happens is that, let me see if I got it here. What happens is when we are, say, bitten by a rabid animal, the virus replicates for a while at the bite site, and it takes a while for the virus to invade our neurons and then travel from our neurons to the spinal cord and up to the brain. From the brain it replicates, and then it will infect the salivary gland, so it can be transferred. But because it takes a while for it to invade our neurons, rabies is unusual in that you can vaccinate after a person has been exposed. And this is so important for us to remember. So Professor Jenna Meyer, who's another of the microbiologists in our department, and Carmen Hercala, who does a lot of our micro prep, they have both been bitten. Professor Meyer was bitten by a ringtail up in Yuba County, and then Carmen, who helps Professor Dave Wyatt with bat research, she was bitten by a bat down in Central America, I think. So because both those mammals are potential reservoirs of rabies virus, and because in both cases, Professor Meyer and Carmen didn't want the animal killed, because usually what they'll do is they'll do like a brain biopsy looking for the rabies virus. They chose to undergo the post-exposure prophylaxis. It's kind of funny, it's like after exposure you're going to prevent it, but it's possible with rabies, post-exposure prophylaxis. But it's important, you guys, that the person goes as quickly as to a hospital right after they're bitten. Don't wait around, don't think about it, go straight to the hospital. Because they need to start this post-exposure prophylaxis right off the bat. And what it involves is multiple rabies vaccines. And in the old days, the old-fashioned rabies vaccine, I remember when I was growing up, it had to be given intraperitoneally, which apparently is incredibly painful. So folks said, you know, it was just horrible, the inoculations. But now, you guys, not a problem. It's an IM vaccination, not bad at all. And then they'll also give you anti-rabies immunoglobulin. So, just as an example, like in some professions, like in vet medicine, if you go to vet school, you always get vaccinated against rabies because your risk is so high of being bitten, right? So you can take serum from people that have been vaccinated against rabies, harvest the anti-rabies antibodies, and then give that passively to somebody that's been bitten. And the idea is those antibodies are going to coat the rabies virus to prevent what? Attachment, right? See, we just see that theme over and over again. If we can block attachment, then we can prevent disease. And then the other thing that we did was a tetanus shot, so tetanus shot, and it was really just in general, you know, tetanus vaccine, and it was really cute. If you talk to Dr. Meyer about it, she said the rabies vaccine was not a problem. She said it was a tetanus shot that hurt a lot, you know. So anyway, just so important though that you go as quickly as possible to the ER and start the protocol to make sure you don't end up with central nervous system involvement. Yeah.
So if you got bit and then got vaccinated, and then say you got bit again, you have to go back and get revaccinated?
If you're vaccinated, like for example, they probably would. I mean, maybe they would shorten the post-exposure prophylaxis, but I think they always want to err on the side of caution. So, that's a really good question. Let me see if I can't find out for you. I know what happens sometimes the neutralizing antibody titer will fall off. And they want your titer above a certain level to be protective. And so what they might be concerned with, depending on how long ago you were vaccinated, they might not know what your neutralizing antibody titer is. So they might say, just to be safe, we're still going to do the post-exposure protocol, which to me makes sense. You want to err on the side of